So, dear colleagues, the first technical break is over and we continue. Under the order issued by the Academic Secretary of St. Petersburg State University as of January 28, the year 2022, number 553/1, I, Alexander Vasilyev, Doctor of Sciences in Chemistry, Professor of the Department of Organic Chemistry of St. Petersburg State University, was appointed the Chairman of the Board. The order also approved the candidacies of other members of the Board, namely Alexey Viktorov, Doctor of Sciences in Chemistry, Professor of the Department of Physical Chemistry of St. Petersburg State University. Sergei Adonin, Doctor of Sciences in Chemistry, Professor and leading researcher at the Nikolaev Institute of Inorganic Chemistry of the Siberian branch of the Russian Academy of Sciences. Ekaterina Bartashevich, Doctor of Sciences in Chemistry, Associate Professor, Professor of the Theoretical and Applied Chemistry Department at the South Ural State University, leading researcher and head of the multi-scale modeling of multi-component functional materials lab. Sergei Kitkov, Doctor of Sciences in Chemistry, leading researcher at the Razovayev Institute of Organometallic Chemistry of the RAS. Valentin Novikov, Doctor of Sciences in Chemistry, leading researcher at the Laboratory of Nuclear Magnetic Resonance at the Nesmeyanov Institute of Organoelement Compounds of the RAS, Deputy Director for Science. And remotely, we have Mikhail Kiselyov, Doctor of Chemical Sciences, Director of the Kristov Institute of Solution Chemistry, RAS. Mikhail, do you see and hear us? Yes, indeed. Alexander Kuchin, Doctor of Sciences in Chemistry, Professor, corresponding member of the RAS, Chief Researcher at the Komi Institute of Chemistry of the Ural branch of the RAS. Yes, hello. Okay, thank you. Yuri Torubayev, Doctor of Sciences in Chemistry, Professor, leading researcher at the Laboratory of Exchange Clusters Chemistry at the Kornakov Institute of the RAS. Yuri, is the connection good? We can't hear you. Turn on the sound, please. No sound. Check the sound, please. So we don't hear you yet. Yeah, now we hear you. Okay, thank you. Hello? Yes, thank you. And Georg Denugula, Doctor of Sciences in Chemistry, corresponding member of the Armenian Academy of Sciences, Professor of the Russian Armenian University, head of the Scientific and Technological Center of Organic and Pharmaceutical Chemistry Lab at the Armenian Academy of Sciences. Yes, hello, Georg? Yes, hello once again. Yes, we're happy to see you. Yes, me too. And our candidate for the degree, Pyotr Tolstoy. I would like to inform you that the panel session of the Dissertation Board is being recorded and broadcast on the St. Petersburg State University website, and it is interpreted from Russian into English and vice versa. Currently, we have an email address posted on the page with live broadcast of the board session, and all listeners can submit their questions to Pyotr Tolstoy online, the questions regarding the thesis or scientific discussion. These questions will allow our listeners to participate in the scientific discussion, and these questions will be forwarded to me by our technical service, and I will read them out during the discussion. The questions must be related to the presentation and the thesis, and don't forget to give your name and position if you submit a question. Questions that have nothing to do with the scientific discussion or dissertation text will not be voiced, as well as anonymous questions. Under the order on the procedure of granting academic degrees at St. Petersburg State University, approved by local regulatory acts, the session of the Dissertation Board is valid, providing 2/3 of the appointed board members are present. The total number is not to be fewer than 4 people. Our board consists of 10 people. Everyone is here today, including 4 members of the board who joined us remotely. And we have a multimedia connection with them, therefore we have the quorum. And I kindly ask the member of the Department of Dissertation Board to support the curator of the defense to fill out the attendance list. Our session should last no more than 3 hours, and the agenda is as follows. First comes the chairman's presentation about the documents submitted by the candidate for the degree and their conformity with the requirements. Chairman's replies to questions, if any, 5 minutes. The candidate's presentation providing an overview and findings of the research, 20 minutes. Questions to the candidate regarding the presentation, 2 minutes per question. The candidate's replies to the questions. Reports on the thesis. The board members will be taking the floor in turns to provide their reviews on the thesis as well as questions, 10 minutes each. The chairman's report on the thesis, also 10 minutes. And the candidate's comments about the reports on the thesis and replies to the questions, 20 minutes. Then open discussion. Speeches of those present at the defense with a brief presentation of their positions or questions or suggestions to the candidate on the topic of the study. 2 minutes for anyone willing to participate. And don't forget to state your full name, academic rank, position and place of work in the registration list, and don't forget to introduce yourself when I give you the floor. Then the chairman will ask the questions submitted during our broadcast via the website. And I would like to draw attention to the fact that written questions that will take more than 2 minutes to read out will not be voiced. Then the candidate's replies to the questions, 5-minute discussion before the open balloting on conferring or non-conferring the academic degree. The discussion of the results is not broadcast. And open balloting, we're going to count the votes and record the results in the protocol. Afterwards, we're going to make a decision on whether to confer the academic degree or not, and finally, we're going to listen to the candidate's closing speech. 2 minutes will be given for that. Dear colleagues, any questions about our agenda? None? Okay. Then the chairman's presentation. Kindly switch off the sound on your mobile phones. And I ask our remote participants to switch off your microphones in order to improve the quality of our connection. And don't forget to turn them on when I give you the floor. Thank you. So, a presentation. The thesis by Pyotr Tolstoy for the academic degree of Doctor of Sciences in Physics and in Chemistry, the specialization 144 Physical Chemistry, is titled Diagnostics of Complexes with Hydrogen Bond and Proton Transfer using Low Temperature NMR Spectra. The thesis was approved for the defense by the order of the Academic Secretary of St. Petersburg State University, issued December 28th, number 13044/1. Pyotr Tolstoy has prepared his thesis at St. Petersburg State University, being a professor at the Department of Physical Organic Chemistry, and he had no academic consultant. 26 published works describe the research findings. 25 articles are published in journals indexed in Web of Science and Scopus, and 1 article in peer-reviewed journals recommended by the Ministry of Education and Science. All the documents submitted by the candidate for the degree comply with the requirements of the university and are found in the certification file. And the curator of the defense, member of the Department of Dissertation Board Support, has all the copies of these documents. And before I give the floor to our candidate for the degree, I would like to ask the members of the board, do you have any general questions to Piotr? Is there any to list the whole, to give the whole list of documents? No. Okay. So, Piotr, you have the floor. Distinguished chairman, distinguished members of the board, I'm very grateful to those who managed to come personally. And I'm very happy to see those colleagues who joined us remotely, distinguished colleagues, dear friends. Before I start, I have a question to the chairman. Can you please tell me, may I take 30 minutes instead of 20 minutes? Well, I believe it's okay for such a thesis, so please, Piotr, you have the floor. Okay, thank you. The work is dedicated to such a sector of physical chemistry as the establishment of interdependence between the structure of chemical compounds and their spectral manifestations. And as chemical compounds, we've chosen complexes with hydrogen bond, and as their spectral manifestations, we've chosen spectra of NMR. And certainly each complex with hydrogen bond has an NMR spectrum. But can we use this spectrum to say something for sure about geometry of hydrogen bond, about its strength, the dynamic of bridge proton movement? It's not obvious. Our motivation when choosing the object of study was functional hydrogen bonds in protons, and one of such protons, photoactive yellow proton, demonstrated here on the slide, will be discussed in the middle of the report. And here the geometry of hydrogen bonds is an active center of the proton. You see interdependence, and it frequently defines the efficiency of the proton. Second reason is polymer materials with the participation of POOH acids. Here we see the transfer of proton, for example, if we talk about fuel cell work. The structure of these cells, the geometry of hydrogen bonds in them, are practically not studied. And isolated hydrogen bonds of different types that can be considered as construction blocks in self-assembly of supramolecular structures processes, molecular recognition, crystallization, and so on. We have our own specificity here associated with the chemical nature of interaction of fragments, with prototropic tautomerism, with salutation of complex as a whole. As a result, the main goals of the study were as follows. First of all, to construct the correlation that connects the geometry of hydrogen bonds and chemical shifts with of the nuclei. Then we needed to create a method of defining relative positions of protons in complexes with several hydrogen bonds. And finally, we needed to construct a model of proton transfer pathway that would take into account not just prototropic tautomerism, but also the averaging effects for chemical shifts using thermal fluctuations of the solvent. And the report is divided into 6 parts. According to the chapters of the thesis, and it will take me 5 minutes to describe each chapter. So let us start with the geometry of hydrogen bond. The position of proton in the hydrogen bond can be measured gradually, and we can shift this position with 2 modes. First of all, discretely changing the substitutes in the interacting fragments and getting snapshots of proton transfer, or with a continuous mode, changing the environment characteristics like temperature. You see this animation, solvent molecules are somehow oriented around this solvent complex. And it's important that in all these processes, the distances R1 and R2 from the bridge proton to heavy atoms are interdependent. And this fact was established experimentally in the late 90s in the works of Thomas Steiner. And you see the list of these works here. And instead of interatomic states, we can use linear combinations. Semi-difference with the coordinate of the shift of proton, and sum the overall length of the hydrogen bridge. And in the process of transfer of proton along the coordinate on the one hand, from one hand to another side, the overall length of the bridge passes through the minimum that coincides with the central position of the proton. And on this graph, you see the data that we collected on the geometry of several hundreds complexes with hydrogen bonds of OHO. And such geometric changes cause spectral ones. For example, the chemical shift of the bridging proton passes through the maximum. The shorter the bond, the larger the shift. So using one distance of hydrogen bond, we can restore the second distance. And the goal of geometry of hydrogen bond is unidimensional. And any of these distances can be correlated with spectral parameters that are unidimensional. These are pure chemical shifts, constants of spin-spin interaction, isotopic effects on them. Figures can be correlated with figures. And in order to construct such correlations, we used an empirical model, the so-called bond order model. And here the distance at the bridge are replaced by exponential distances that are called bond orders. And the parameters in these exponents are chosen in a way so that across the path of transfer, we see the equality of 1 to the sum of parameters, as like valencies divided into between the two bonds that it forms. And during the shift of proton, one of the orders drops and another bond order rises, but the sum remains the same. And we've demonstrated that the chemical shifts can be represented like simple functions of the bond orders. For example, the chemical shift of the bridge proton. And here you do the following thing. First of all, you take asymptotic values of the chemical shifts, the chemical shift of the free donor, and the chemical shift of the free acceptor. And their contribution into the resulting shift is represented as proportional to the appropriate bond orders. But this pumping of shift from one extreme value to another, especially in this example where they coincide, poorly describes the reality. Therefore, empirically, we add up a third summand proportional to the bond order product. And that is supported by experimental data. As a result, we got a 3-parametric model, and 3 parameters are independent and measured experimentally. 2 marginal asymptotic values and 1 maximum to achieve. And such correlations, parametric correlations in the work, were constructed for a range of complexes. First of all, anion complexes with intermolecular hydrogen bond or with intermolecular hydrogen bond covalently joined to counter ions, or with a free counter ion but homoconjugated, or with free counter ion or with heteroconjugation. And electroneutral complexes as well of base ace of the acids. And, for example, cases where different acceptors and 1 donor. Carbonic or phosphinic acids. The correlations were constructed and used for proton chemical shift, for chemical shift of carboxyl carbon, for phenyl carbon, heterocyclic nitrogen atom, or spin-spin interaction with proton. HD isotopic effects on the chemical shift of carboxyl carbon, chemical shift of phosphorus hydride. So here you see the examples, the change of chemical shift of phosphorus in phosphinic acids along the shift coordinate. You see the sigmoid form. And to the right, you see how HD isotopic effect changes on the chemical shift of carboxylic carbon. So this the shift between the deuterated and protonated complex. This is a kind of dispersion curve, and that's the difference of 2 sigmoids. So that's for homoconjugated ions of carbonic acid complexes. And all the correlation can be substantiated like that. Spectral NMR parameters can be divided into 2 classes. One class is made up of parameters that change along the coordinate, and they change monotonously between the 2 asymptotic values. Such dependencies are well described by 2 parametric correlations, and these parameters reflect the level of shift of proton, and they can be used for definition. And first and foremost, these are chemical shifts of nuclei directly participated in bridge formation on the neighboring ones, and also the constants of spin-spin coupling with one bond. And another class is made up of those that change through extremum for short hydrogen bonds, and this is described by triparametric correlations. These parameters reflect the length or shortness of hydrogen bond, and they can be used to assess it. And this group includes chemical shift of the breaching proton, HD isotope effect on it, and spin-spin coupling constant with two bonds via hydrogen bridge. And in order to measure these parameters for hydrogen-bound complexes, we need to increase the lifetime. Otherwise, in NMR spectrum, we have this scattering of information due to averaging effect. And in order to register such on average spectra, we use low-temperature NMR spectroscopy. And briefly, what's the idea here? The spectra are registered for samples in solvents, in liquefied deuterated gases, freon gases. Sample preparation is conducted in special ampules that withstand pressure of several atmospheres, but we managed to conduct experiments lowering the temperature up until 100 degrees Kelvin, and at this temperature they still remain non-viscous and liquid solvents. And it should be mentioned that the pressure in the ampule and the temperature in spectrometer go beyond the margin, the extreme allowed by the producer, but if you work accurately, nothing explodes. And using such an approach, we managed to shift equilibrium to complex formation, and second, slow down molecular and proton exchange. Therefore, in the spectrum, we see the divided signals from complexes with different stoichiometric content, different isotopic content, and structure. Using this approach, we can be demonstrated on a well-studied effect of self-association of acids and cooperativeness and cooperativity of hydrogen bonds. And here I refer to the sensitivity of one hydrogen bond to the change of geometry of the neighboring bond. And as a perturbation of changing geometry, we offered to use its weakening using deuteration. And then we can consider examples of acidic acid complexes. To the left, you see cyclic dimer of the acidic acid. And here in deuteration of one hydrogen bond, it's weakening and extension. The second one is also weakened and extended. And its proton resonates in a higher field compared to the initial signal, thus supporting this idea of cooperativity. And vice versa, in homoconjugated anion of acidic acid, as to the right, two molecules of acidic acid compete with each other for one central anion. And weakening of one hydrogen bond due to deuteration strengthens the neighboring one. And proton chemical shift of the remaining proton in this half-deuterated complex is found in the weak field compared to the initial signal. So in quality, in the sign of effect, we can differentiate cooperative interaction of hydrogen bonds characteristic for complexes like head to tail from anti-cooperative characteristic to complexes head to head, competing complexes. And in the number of vicinal effects, such effects were called vicinal. And in their number, we can judge about the stoichiometry, about the number of hydrogen bonds in the complex. Vicinal effects we use to study the structure and of a range of complexes, homoconjugated ions of phosphinic and phosphoric acids, this complex of hydrofluoric acids, zwitterion complexes of carbonic acids with pyridines, carbonic acids with pyrazoles, several complexes with intermolecular hydrogen bonds, cyclic dimers of benzoic acids concluded into self-assembled capsule that is depicted here as dotted line, and some other systems. But I want to dwell upon two examples that were not shown here, the use of vicinal isotopic effects. First of all, self-association of phosphonic and phosphoric acids. Phosphonic and phosphoric acids form two types of self-associates. Stoichiometry can be established using vicinal isotopic effects. And after partial deuteration, the signal of one self-associate is divided into two, and that's a cyclic dimers. And another signal is divided into three, and that's a cyclic trimer. They have more topologies. And this trimerization is demonstrated by different phosphonic and phosphoric acids. And if we mix them, we see the formation of a cyclic tetramers of a mixed type. And I believe that they are stable due to small loss in entropy of the molecule. You know, these molecules preserve a lot of mobility. And phosphonic acids gather into a fixed tetrahedral tetrameric capsule. And here it is strongly distorted in order to see all the molecules conveniently. And that's enthalpy when 8 hydrogen bonds per complex. And the second example of using vicinal effects are models with active scent of photoactive yellow protein. Photoactive yellow protein is the primary receptor in purple bacteria. They feel blue light, and presuming that there is ultraviolet there, they feel negative. They undergo negative phototaxis. They hide in the shade. The absorption of quantum of blue light in this range happens in cofactor of thioantheri parachimerinic acid, thioester. So you see the protonation here and the formation of hydrogen bonds with branch chains of amino acids. And some people asked, why is this strong donor of proton and why it does not give it to the strong acceptor? And in order to think about it, we synthesized a range of model complexes that model either one hydrogen bonded complex, this blue one, or this red one, or both at a time, or 3 at a time, green, blue, and red. And using NMR spectroscopy and ultrasound and ultraviolet, we managed to prove that strong donor protonates strong acceptor, but it does not do it if on the opposite side this oxygen is already involved into a weak hydrogen bond with a neighboring phenyl oxygen and OH group. And as a result, we have a chain of anti-cooperative hydrogen bonds that compete for the central oxygen, and as a result, none of them can give the proton to it. And anti-cooperativity of these bonds, so the sensitivity, the residual sensitivity to the geometry of each other is demonstrated on the negative HD isotopic vicinal effects. And what I liked most is that it was demonstrated using the same method on the protein itself in the group of Professor Hashwood in the United States. So these negative HD isotopic effects were demonstrated, and Professor Hein group in Germany used mutant form of protein where one hydrogen bond lacks due to the fact that one amino acid was replaced by another. So they demonstrated that when the second bond is eliminated, proton returns to phenyl. And that was done by our advice. So that's enough about vicinal effects. And now let's talk about another quality characteristic used to judge on geometry. That's the primary isotopic effect, and it can be demonstrated using the example of homoconjugated complexes of carbonic acids. And here on the slide you see a series of such complexes. And to the left, you see deuter and proton spectra. And in all cases, even in strong bonds, a deuteron is more screened than proton. And in continuous approximation of atoms of oxygen in this bond, this effect drops, and for extremely hard bonds, this sign changes to the opposite one, and we associated it with the shift from double well to single well potential and to single maximum wave function of the bridge particle. And the reason of changing the sign on the chemical shift in the isotopic effect is in a double well potential. Most probable position of protons and neutrons differ due to harmonicity. And as we observe the chemical shift, which is a folding of function of the chemical shift with a wave function with the nuclear wave function, the chemical shift of protons and neutrons are averaged on different lots of this curve, and we get a negative isotope effect. And when we shift to single well symmetric potential, most probable positions of proton and deuteron coincide, and the width and amplitude of fluctuation is more important. Deuteron has a lower one, therefore the averaging happens along the smaller curve, and the isotopic effect changes the sign to the opposite one. So in quality, we can differentiate the central symmetric position of the proton from the jumps of proton between the two positions on both sides of hydrogen bond, even in a case when freezing is not possible, even in freons. These proton jumps, however, are slow if we talk about optic spectroscopy. And studying them as the entire pathway can be done using combined UV and MR spectroscopy, where we use both methods with difference in characteristic time. And we modified an MR spectrometer and constructed such an installation using customized sensor. We attached lighting illumination to the bottom, and part goes through the thickness of the solvent. It is reflected from Teflon, goes to optic fiber, and goes for analysis. Like that. Thus, we register the NMR spectrum and UV spectrum of absorption for the same sample at the same period of time, the same concentrations, the same temperature. So the joint spectral data, and they are so joint that we managed to construct two-dimensional correlation spectra based on Hilbert transformation. On one axis we have an NMR spectrum, and the other axis shows UV absorption spectrum. And these cross peaks on this two-dimensional map mark signals of the same compound, of the same complex with a hydrogen bond in NMR and in ultraviolet. And this simplifies referencing spectra in both cases, depending on where it's easier to do. And using that new spectrometer, we studied a range of complexes of phenols with different acceptors of carboxylate anions. And during the transition of proton through the center, when proton shift passes through the maximum and forms a very strong bond, in ultraviolet spectrum we see prototropic tautomerism. And the shift of equilibrium is not just the shift of proportions of one or another tautomer. That's a shift where the geometry of each tautomer is changing as well, and this can be demonstrated with this scheme to the right. But this equilibrium between two tautomers with a practical central position of protons in each of them, and these oxygen atoms are so close and two minimums between them cannot be generated. Therefore, this fact requires explanation. And it seems to us that we found this explanation analyzing solvitation effects. We calculated initial molecular dynamics. Here you see the example for complexes of phenol with carboxylate anion, and such calculations reproduce the shortness of hydrogen bond and continuous shifts of jumps of proton from the center and vice versa, and to maximum distribution of most probable proton positions. Both of them are close to the center of the hydrogen bond. The asymmetry is negligible. And at that, each tautomer, each maximum, is represented by Salvator ensemble. That's the structures that are different at once, and individuality is a bit scattered, you see. But analyzing the structure of salvation shell, we showed that the moving force of the shift is the formation and breach with CH groups of the solvent. When this hydrogen bond with free carbonyl is formed due to anti-cooperativity of the bond, the proton shifts to phenol, and as soon as this hydrogen bond breaches, proton gets back. And at that, along all the steps, we see interdependence of two distances of hydrogen bond. We see the correlation of this position of proton with a chemical shift. And averaged value of the chemical shift coincides with the experimental one pretty well. And such specific interactions with solvents that cause the shift of proton can be also found for halogens, and this was demonstrated on the last slide using the example of central symmetric anion FHF in tetrachlorine carbon. Here you see numerous halogen bonds, and the predictor for the shift of proton is the disbalance in the number of these bonds to the right and to the left. More bonds to the left, proton moves to the right, and vice versa. And once again, we see interdependence of distances in the hydrogen bridge and their connection with other chemical shifts. And this brings me to conclusions. There are 6 of them, and I'll shortly list. There are 2 technical achievements along the way we use low temperature NMR spectroscopy in liquefied gas freons, and we've constructed new spectrometer to measure UV and NMR, and 4 conclusions on the geometry of hydrogen bonds. This sign of primary isotopic effect can differentiate the central position from non-central one. Vicinal isotopic effects allow us to differentiate cooperative interaction from anti-cooperative one. And in the number of effects, we can decide on the stoichiometry. Then we got a range of correlations between the position of bridge proton and the chemical shifts of the surrounding nuclei as participating in hydrogen bond or the neighboring ones, and we constructed the proton transfer pathway, including tautomerism between 2 forms with very strong hydrogen bonds, nearly centrally symmetric, the existence of which was explained by thermal fluctuations of specific interactions with molecules of solvent in the first salvation shell. And that's it. Thank you. Thank you very much, Piotr. Please, dear colleagues, questions on the report, questions on the presentation. No questions. I didn't have this question in my report. That's a technical question. Your brilliant installation for the registration of UV and NMR. The use of Teflon insert, that's a really cunning approach, but it adds up diffusion barrier to the ampule. The molecule under the insert, it can defund to the solvent, and at the same time, the ampule cools down with the flow of nitrogen, and it's sufficient to span 10 minutes, so the temperature would be leveled up. But this insert may lead to the fact that molecule under the insert for the registration of UV spectra is not in the same conditions as in the middle. Therefore, the question, did you try to conduct a simultaneous calibration using some compounds that can provide the necessary results both for UV and for NMR? We did not use calibration, but rather the following technical approach. We changed the form of this insert in order to ease diffusion. We waited more. We wanted to see whether there are some temporal changes, whether they are ongoing, not calibrating with Kelvin, but just watching if anything changes at all. And our conclusion was as follows, that if we are on the side of overkill in time before the cooling and measurement, it is enough for those inserts that we used. On the scheme that I've shown you, and on the photos, on the side photos, we had old inserts, the so-called old inserts, and the new inserts had additional cuts in order to secure more space for the circulation of liquid. And the point that we need is very small in the center. Therefore, we could, cut this insert without loss of NMR spectrum and without visible change of anything else. And it seems to me that our conditions were sufficient. We waited for 15 minutes. Thank you. Peter, other questions? Yes? Thank you so much for the brilliant presentation. Can we get back to the 8th slide? Brilliant. This empirical term, P1 plus P1 and P2 is empirical. Yes. So, taking into account the volume of experimental material, didn't you want to try to give this data to machine learning in order to find some mathematical models, some other mathematical models beyond this that prove to be valid? No, but not because we decided not to do that. We just didn't think about it by then. Efficient use of machine learning, in fact, requires sufficient testing set for the system and the set of an additional initial training. I don't think that we have enough data to do it efficiently. Just rechecking simple polynomial terms that can be considered as term expansion into indefinite range. So this was enough. And the scat of experimental points is sufficient, and Sergei mentioned it in his review. Therefore, choosing something more complicated than just the product is, unnecessary. We have the scatter of experimental points around the curve. Did I answer your question? Yeah. Other questions, please? So, I wanted to ask the following thing. Hydrogen bond can have an angle that is not equal to 180 degrees, and in the thesis you considered and explained it. You did not explain it in the report. Can you please mention that, whether this angle of hydrogen bond influences these correlations, and are there any underlying problems here? Thank you very much. I had several of such questions. I did not cover it in the report because it was lengthy enough, but I'll comment right now. Experimental data that demonstrated the possibility of this equation that I show on the slide is based on the range of complexes that includes nonlinear hydrogen bonds. And the angle of the bond in this set is not 180, but also 150 up until 130 degrees. And in this range, the interdependence of interatomic distances from the proton and from proton to acceptor is still preserved. And on the left graph on this slide, you see the points, not just for linear hydrogen bonds. And non-linear hydrogen bonds are not necessarily the ones that are most deviated from the curve. And this interdependence stays empirically. Therefore, all the correlations that with chemical shifts, they stay in the same range of angles as initially, plus minus 30 degrees. Did I answer the question? Yes. Yes. Thank you. Thank you. Other questions? Maybe the colleagues who joined us remotely? No questions? Brilliant report. Okay, let me ask then. Petr, your main method is NMR on different nuclei. If you have a choice, you can use spectra of protons, on phosphorus, on nitrogen, on carbon. Which method is best to ensure best results for your work? It's hard to answer straight away, but I'll try to. First thing is where is the proton, or how short is the bond? It's divides parameters at once. And if you choose one question, certainly it's better to use those spectral parameters that give intensive signal to the noise, and a huge difference in values from short to long bonds. So the spectral set. And if you can mark with nitrogen and 15, yes, you should use it if it participates in the formation of the hydrogen bond. And if you don't have such an opportunity, you use what you have. Proton, carbon, phosphorus. Nearly the same information, just proton is a bit easier. You cannot but register proton cycle if you start doing NMR. Fluor is a good nucleus, but we don't have a lot of long-standing bonds. It has limited chemical applicability. But if that's your topic, then you're lucky enough. So, because it's very sensitive to the formation of hydrogen bond. Okay, thank you. Well, the installation with illumination, you simultaneously give light and it is reflected at once, yes? And then you mathematically process it, yes? It's done in real time, okay. And as for salvation effect, slides 31 and 32. Dichloromethane is a donor of hydrogen here. How strongly it can form hydrogen bonds? It's not chloroform. Well, it can do that, yes. That's a weak hydrogen donor. It does not form halogen, strangely enough. It's not a donor for halogen. And in salvatomers, a CH donor ability wins. Okay, other questions? Anyone who wants to ask a question, you can introduce yourself and ask questions. Yes, Alexei, please. I have a question on different terms that you mentioned. In one, you said that entropy wins, and another one, enthalpy. Did you conduct some quantitative assessment? For quality, I understood it. As for quantity, do you have any quantity data to support it? Did you calculate? We calculated enthalpy, good strength for hydrogen bonds, so everything was clear here. As for the enthalpy, I don't like enthalpy calculations that were ensured with quantum chemical methods. Yes, I misspoke. I didn't like the entropy calculations, because that mobility of molecules in complex is a strong amplitude fluctuation that does not suit to any fluctuation mode to calculate. Therefore, it was intuition. Dear listeners, I see chemists are asking questions and physicists. What about you? Okay, as there are no questions, yes, let us shift to our reviews. Taking into account that all the reviews were already published on the university website, everyone could read them. Therefore, you can give just basic points in your review, the relevance of the study, the importance, the value, and your questions. And we need to decide how the applicant is going to answer the questions, maybe after each review. Yes? Piotr, do you agree with that? Yeah. Well, there's no need to read them. By the way, I have 10 pages of answers. So we thought everyone read each other's reviews. Okay. Now, for every question will be read, and you will provide answers. So now I give the floor to Alexei Viktorov. Yes, thank you. I will not read. To my mind, our today's session is very peculiar. It's not a qualification board. It's, a kind of right. Because indeed, Piotr is a professor that whose achievements are universally acknowledged. He has global recognition and contacts. He's very well known across the world and in our country as well. He has a huge group that is actively working with a lot of grants. Therefore, for this short, happy time, within this short and happy time, when we work together, I frequently forgot that he is not a doctor. But still, that's a right, as you have it. Therefore, I won't read my review. Certainly, I described the relevance, the scientific novelty, the validity of results, and the substantiation of conclusions, practical value, and the remarks, critical remarks. So may I read them? For the examples you mentioned in Chapter 5 of the distribution of geometry of hydrogen bond, you mentioned Salvator-Mayer ensemble that are different with by specific interactions between the molecule of solvents and the dissolved complex. The role of reaction field of the solvent, taken into account in continual models, like polarizable continuum model, is not explained. Can you explain reversible prototopic tautomerism with oscillations of electric field of the solvent? Second question, based on the results in sections 3.7, 8, and 9, we can conclude that P31 shift is not that informative for the diagnostics of hydrogen bond chemical shift, because it responds to some side factors without the change of geometry of hydrogen bond. So what are the practical limitations here for for equation 3.5. However, we can conclude that the thesis of Pyotr Tolstoy meets the requirements of the order on the procedure of granting academic degrees at St. Petersburg State University. And Pyotr Tolstoy deserves the academic degree of Doctor of Sciences in Chemistry in specialization 144, Physical Chemistry, and Articles 9 and 11 are not violated. Thank you, Alexei. Dear members of the board, the conclusion should be read for sure, yes, for the protocol. So, your answers, Pyotr. Thank you, Alexei, for the comments. You forgot that I'm not a doctor, but others, told me about that all the time. So the answer is as follows about the position of the bridge proton. Initially, we presumed that this effect will be a decisive one, and we started these calculations like that, but it turned out that it's not. The electric field in the center of hydrogen bond, calculated by cutting out of the complexes and summing up of electric fields from all the charges in the salvation shell, was weak. And compared to the fact that we have from specific interactions, it did not play a role. And I believe that if we chose liquid neon as a solvent, maybe the electric fields would remain the only factor, and in this case they would be more decisive. Yet in our case they were not decisive, but we made these assessments. The second question about the practical value of correlations with the chemical shift of phosphorus. Well, I believe this practical value is limited because intuition says it that when we change specific compound, mostly phosphorus nuclei, when we change aggregate state or chemical nature of complexes, the trends will be the same. Functional dependencies, mathematical equations will be the same, and large-scale coefficients will deviate. For a specific system and numerical assessments, we will need to recalibrate this curve all the time. And it will remain the same. It is likely to remain the same. So that's limited value for that. Next review. Sergei Adonin, please. Distinguished colleagues, I will support the opinion of my colleague because I really agree with the fact that today that's a kind of right, a kind of ritual, rather than defense. Therefore, I needed to make an effort to write this phrase that is a qualification work. And I believe many of us will agree that quite frequently when we talk about qualification work, we think about something like, oh, he finally reached this level. But right now we're talking about a different thing. That's an outstanding in-depth research and a new scientific field. When at some time we talked about doctoral dissertations that are very scarce and are very limited, so that's a very in-depth work. I won't list all the advantages, though experimental innovations that were introduced, they already deserve a lot of support, and I will not be surprised if equipment producers already think about commercialization. You mentioned the fact that out of 26 articles, 4 were published in the Journal of American Chemical Society and 2 in a very high-profile journal as well. It demonstrates the level of study because we know how hard it is to publish in these journals, and it means that the articles got a lot of peer review, and it means that the author can answer all the criticisms when publishing such articles. And I cannot but mention that the thesis is written pretty well, though, you know, we know the surname of Piotr, and I'm not talking about the volume, like a typical Tolstoy volume. And such a volumetric text, you know, is very pleasant to read because that's a brilliant Russian language. It's rarely seen today, but still everything was wonderful here. I had one remark that I wanted to read out. In the very beginning, when Petr discussed geometry of hydrogen bonds, he wrote that interatomic distance A proton and B proton is interdependent. It's clear that the character of this correlation is the topic of the study, but strongly saying that there is an interdependence here, it's trivial, you know, geometrically, because we understand that the distances A and B are finite. Therefore, this interdependence cannot but be found here geometrically. So it's clear that then we'll talk about the character of this interdependence, but that's just a trivial note that I found funny. And I had no other criticisms, though it was my duty, and I had no serious questions to you. And in order to stick to this right that we have, I need to say that a thesis by Tolstoy is a qualification work performed at a high professional level, and the thesis by Piotr meets the requirements of the orders of November 19th, 2021, number 118 1/1 on the procedure of granting academic degrees at St. Petersburg State University. And Piotr Tolstoy deserves the academic degree of Doctor of Sciences in Chemistry in specialization 144 Physical Chemistry. And Articles 9 and 11 of the above-mentioned order are not violated. Thank you. Thank you. So, Piotr? Thank you, Sergei. You mentioned commercialization, volume, and distance in the hydrogen bridge. As for the commercialization and volume, other reviewers mentioned that as well. Commercialization is an interesting story. We addressed Brucker and the Free University of Berlin, where I worked by then, and we asked to patent and commercialize. Brucker said that the technology of experiment is not foolproof, and users will not be able to work with this technique. And the Free University of Berlin said that to support patent we need money and potential commercialization, and Brucker is the only one who can buy it, this technology. Therefore, they will not sell it. Therefore, everything remained as such. We had no commercialization. Or maybe Brucker secretly decided to create a new device. As for the volume, I can just beg pardon for that I forced you to read so much. And now, reconsidering the results, it seems to me that I could cut off 100 pages without any loss of sense. But at that point, it was very hard. Well, that was not criticism, but I still believe that you're right. This could be a criticism. And as for this distance, basically the character of this dependency is specific. The change of distance differentiates weak nuclei from the strong ones. Therefore, when one distance expands and another one reduces, that's trivial. But when the fact that it always happens when short becomes longer and the sum drops is a less trivial statement, and that's the character of dependency that you mentioned, that the work needs. Because if we didn't have it, we would have one thing. Either all hydrogen bonds would be of one length, or we would lose the unique mutual interdependence of these distances that we need to reduce the dimensionality of the problem. And we still have these correlations, numerical correlations, and I believe you'll know it quite well, but I needed to comment on that. Thank you. Thank you, colleagues. If you have several questions, we can ask Piotr to answer each of the questions at once. So, please, Ekaterina Bartashevich. Distinguished Chairman, distinguished members of the board, my impression on Piotr's work, I'll try to describe them briefly. First of all, this work is very variable. He did not just study numerous objects of study, organic compounds, but he also considered novel experiment technology. He studied physical chemical characteristics in different conditions, NMR spectroscopy parameters, and also in the thesis he used modeling of systems and quantum chemical modeling, and he used quantum topology, analysis of density, both experimental and technical and theoretical aspects of the scientific work covered and concentrated on the central, focused on the central problem, the diagnosis of structural characteristics of hydrogen bond, bridge bond, associated with the data that we obtain in low temperature studies using NMR spectroscopy. And regardless of this varied character, we still have a unified line, to my mind. It brings many aspects of this work together, and namely that's the use of a simple model based on bond orders that allows the author to bring NMR parameters together with long and structural peculiarities of the hydrogen bond. That is why for my first question, and I believe you can answer both at once, both of my criticism at once. So I'll start with a question. So this a difference in the objects of study, their state, cooperative and anti-cooperative bonds, central position of the proton and its typical position. And at that, the systems can be either different or unified. And talking about the fact that you consider functional materials where the proton transfer can play a significant role. For example, in possible coexistence of some situations and structural peculiarities. The parametric model is simple, and here's what makes it convenient. And any parametric model, as we know, makes us be careful about the transferability of these parameters. They can depend on the sort of, on the type of bond, on its peculiarities. So the question is, for different systems, how much this transferability of parameters is possible, and is this methodology suitable for the comparison of results for different chemical systems and conditions? That was the question. And as a criticism, can I answer it once? Yeah. Okay. Geometric interdependence of hydrogen bond. It stays there when we change substitutes in molecules, when we transfer protons in quantum chemical calculations and fluctuations of the environment. So that's a kind of robust regularity. That's a geometrical regularity. And if we talk about NMR parameters, you're right, these parameters are more prone to change when the system changes. But NMR parameters are essentially local. Therefore, the local density stays in changing environment. Where it stays, the correlations will stay as well. And I see two sources of strong changes of system parameters. These are weak hydrogen bonds, and I had few of them. Luckily, when a lot depends on chemical shifts of monomers, sensitive to substitutes, because there you have a lot of dispersion there. And those cases, when there is a huge contribution of magnetic anisotropy, we have an aromatic system nearby the bridge, and to all chemical shifts we add up some numbers. And in this case, the parameters start changing. But in other cases, indeed, every model has applicability limits, and starting with attentive consideration, our model stops being applicable. But that's a guarantee of work for the forthcoming years, you know. Okay, I'm satisfied with the answer. So I had another remark and the final part of my review. Certainly hydrogen bonds are specific interactions. However, we have something else in the systems that you considered. And Peter drew attention to hydrogen bonds, because here it's an important component of the system. In the thesis, he mentioned deuterated chlorine. And also in the system, we saw interactions that can also be described as specific non-covalent bonds on the principles of donation of electrophilic site. And if we continue such connections from halogenous ones, I paid attention to the fact that interaction with he had also this interaction described for so these nictogenic bonds should be described. So these are, you know, some private criticisms. And Sergei praised the text, and let me praise the graphics. I was really pleased to see the original graphics of some of the results, and certainly the graphics was very clear, and sometimes it helped me to differentiate between the nuances. Thus, I believe that the thesis considers the basics of the concept that defines the interdependence of structural and experimental parameters of low temperature NMR for chemical systems with bridge hydrogen bonds. And this concept can be considered as an achievement. And the methodology for proton shift and credible description of hydrogen bonds in liquid environments can be qualified as a new scientifically substantiated solution. And this is by Pyotr Tolstoy. Meets the requirements of the order on the procedure of granting academic degrees, and Pyotr Tolstoy deserves the degree of Doctor of Sciences in Chemistry in specialization 144 Physical Chemistry, and Articles 9 and 11 are not violated. Thank you, Ekaterina Vladimirovna. So, Piotr, can you please comment? I will answer like that. Indeed, for sigma-wall interactions, I didn't have time to describe. And halogenic bond is, a free rider there, because I could not but mention it, talking about tetrachlorine carbon. But I did not pay a lot of attention to it. Therefore, just to explain myself, I can say that after I stopped working on the thesis, my colleagues and I continue working on additional publications dedicated to halogen bond, and we used your approaches, but we did not tell that to you and before. So I hope we'll tell about it later. So till the end of the year, we will publish an article on this issue. Okay. Okay. Next review, Sergei Kitkov, please. Yes, dear colleagues, hello. Once again, here after several members, it's hard to add up something new to the positive characteristics of this work, but I'll still say that the relevance was mentioned quite well. And the report, and on the slide that we see here, we see there's objects of study where these hydrogen bonds play a role. And taking into account the fact that right now we see a rise of works that are dedicated to this, an influx of works that are dedicated to this topic, it means that new aspects open up, and the role of hydrogen bond is in different fields and materials and supramolecular chemistry and in other fields is very important. And talking about this work, we cannot but mention the fundamental approach that the author uses considering all the issues. He focuses on such nuances of different regularities that it really creates a very good impression. And this work certainly has new original approaches, including the ones that are very powerful, that can be grouped in and include several items and several subjects of study. So here we talk about different bond orders, we talk about NMR spectroscopy methods in freons with low temperatures, and the technique of registration of electronic absorption spectra. So this gives contribution to methodology. This provides a huge contribution both to the methodology and to applied studies. So there are no questions about scientific novelties. It's quite obvious, as well as the contribution. As for the practical value, I wanted to say that the considered aspects associated with the functioning of proteins, I believe, and that's one of the fields that reflects the practical importance of this work. And as for the drawbacks, the main phrase is that there are no serious drawbacks in the thesis. However, there are some technical remarks and questions that I had while reading, and I will list them right now, but as the most negligible ones are not interesting, I will group them. So the first remark is about the correlation between spectral and geometric parameters of the studied systems. For me, it was not clear how you fitted the parameters in correlation equations. Did you use regression analysis here? Because sometimes I have questions on the accuracy of defining geometry of the bond and reliability of correlation curves. On a range of images, we saw that points are deviate far away from the curves, and the author assessed a mean quadratic deviation as 0.02 angstrom. So is this assessment then substantiated when you talk about 1/1000th angstrom accuracy? Therefore, sometimes while reading, it seems that correlations are based on limited points or points that are located very close to each other. So the question is, what's the reliability of this construction? So, Piotr? Well, you see, as for the figures of the dot, so I'll just agree with you about it, because we value these figures up until the digit when that start changing. Because when we consider 1,000th, it means that we need to approximate. And as for regression analysis, I used it in a range of cases. So I used minimal square approach. But sometimes I had no place for fitting. I had experimental data on maximum chemical shifts and marginal chemical shifts. And in this case, I had nothing left. But this does not eliminate the scatter of points around the curve. And what you mentioned in the review, the assessment of reliability is something that I can just agree with. Any narrow range shows that the accuracy of values stays at the level of some hundredth of angstrom. And it seems to me that relative accuracy of correlation is higher than the absolute one. And in homologous series and isotopologies, series of the same complex, the relative changes of chemical shifts using these correlations more accurately shift to the distance than absolute values to absolute distances. Therefore, frequently absolute error is not given in order not to create impression that we cannot just define the sign of isotopic effect, though it is taken directly from the spectrum and it is more accurately than the scatter that we take along the set of complexes. But the question on the accuracy of measurements really arises. And I should have described it in more details, I believe. I should have mentioned how we assessed accuracy, where we use assessment and where we use relative values. And certainly I should have paid more attention to the description of errors. So that's how I commented. Okay, thank you. And you said that at some point the correlation is based on a number of points. In some cases it is not constructed on these points, but we had a previous correlation that was applied to this point. So these points are applied to this curve, and the curve was taken from the previous studies. Okay. The second group of which is associated with quantum group of quantum chemical calculations. But for some groups and compounds, I wanted to ask the following thing. You lack some calculations for compounds 91 to 105. That's chapter 4. And it seemed to me that it would be more demonstrative if you would study also the distribution of charge and the change of charge during migration of proton along the hydrogen bond. And also the question on the energy. It's unclear what kind of energy you describe, electronic, but plus ZPE, enthalpy, or Gibbs energy is associated with isomer stability. And the same question is about the energy of complex formation of hydrogen bond and activation energy. Well, I'll start with the last question on energy. In every case, I refer to full electron energy without and in complex formation, we also talk about full energy without error of fluctuation, and taking into account the energy of monomers. And salvation with polarized dielectric is sometimes considered. So I could have written that more accurately, so I agree with your comment. The second point that you started with, whether I conducted the calculations of partial charge for atoms. Yes, we did it, but they were not quite informative. In some cases, they just described what we expected to see, how the charge shifts when the proton shifts from one part of the bridge to another one. But we were worried about the number of artifacts in these calculations associated with the fact that ideal partitioning system in electron density for atoms does not exist. And frequently we have some non-chemical figures when we calculated partial loads on atoms. So we started to avoid them at some point. But we had successful cases as well, for example, for hydrogen bonds with CH group and the transfer of proton with the formation of carbon ion. But unfortunately, these works were not included in my thesis, therefore. That's it. Okay, thank you. And other remarks are pretty technical. They are dealing with those differences and some imperfections that I saw in captions and so on. So there are some differences in data with captions. In some place you write that complexes are intermolecular. So when you look at these complexes, one of them is not, and enumeration of compounds differs. And one place I want to comment on it separately. On page 343, you have a picture and drawings, and they are defining the coordinates of Q1 and Q2. You know, there's a difference. In the text you describe it differently, and on the figure you have something else. So you have trajectories that are defined with different colors, and when you see the description in the text and what's real, it turns out to be vice versa. So these are technical remarks. Yes, I would like to comment on that. Well, certainly I agree with all these imperfections for numerations and axes and whatever. I agree with all of them. And I hope so. You mentioned this red and blue on this curve, and finally I hope that I place these figures correctly. And as for the technical imperfections, well, summing up, you found a lot of mistakes, more than anyone else. And if I sum up everything that everyone found and presume that I have 2 times more mistakes, because I believe in myself, you know, it turns out that I have one imperfection per 20 pages, but that's a point for further statistics. Well, all the mistakes are really made by me, so yes, I beg your pardon for that. Okay, thank you for agreeing with these remarks and with the ones that would follow, because I will not read all the technical points, but I wanted you to comment one of them. The idea that in the less polar environment, the acidity of phenol increases compared to the acidity of phenol acid. I wanted you to comment on that because it contradicts with experimental values. Well, acidity is incorrect here. That's proton donor ability. And the shift of proton to one side or another can be associated with a change of proton donor and proton acceptor abilities of the interacting fragments. Therefore, in this case, the phrase was to describe the observed situation, whether this ability drops or not. And initially, I did not plan to write about acidity as a constant of the thesis in a solvent. That is why I need to take away all these words on acidity and instead write proton donor ability. Okay, Sergey, is that it? Okay, then your conclusion. Okay. Certainly these questions are all technical ones, and they do not compromise the overall high value of the work that can be assessed as a combination of results. It can be considered as a huge academic contribution in physical chemistry. And I have no doubts about the credibility of results because Piotr used very well-checked methods, and we see the coordination of experimental and theoretical data. And finally, I can conclude that the thesis by Piotr Tolstoy, titled Diagnostics of Complexes with Hydrogen Bond and Proton Transfer Using Low-Temperature NMR Spectra, meets the requirements of the orders of November 19, 2021, number 11181/1, on the procedure of granting academic degrees at St. Petersburg State University, and Piotr Tolstoy deserves the academic degree of Doctor of Sciences in Chemistry in Specialization 144 Physical Chemistry. And Articles 9 and 11 of the above-mentioned order are not violated. Thank you, Sergey. Next review. Valentin Novikov, please. As Sergey mentioned, when you deliver your speech later than colleagues, you want just to add up a bit and shift to the conclusions. I wanted just to say a few words as a spectroscopist. The thing is that the work that was conducted requires not just academic vision and good qualification, but also some scientific, boldness. Now, it was already mentioned that the installation was recognized as not foolproof by Brucker, and operational conditions violate the requirements of the producer. We need to understand how significant these violations may be. The majority of experimenters do not go lower than minus 70 or 80 Celsius. And only if they're bold enough they do that, because in many cases the standard sensors that we have may freeze, and at that vacuum is no longer there, and we may have certain technical problems, and some labs have already faced them. Therefore, such wonderful experiments that are described in this thesis are not conducted because people are afraid of them. And all experiments were conducted in thick wall ampules because there was very huge pressure there, and in addition to freezing, we also had a risk of explosion of the sensor. And there's a wonderful phrase there. We did not have a lot of explosions along our work. So the probability of explosion was enough not to conduct these studies. But as I've already mentioned, academic boldness is pretty high for Piotr, because the current adrenaline was not enough, and he decided to take away the bottom and stick on quartz on it. And when I read up until this point, I thought that I would never allow anyone to touch my equipment with such an approach, but it turns out that it all ended up successfully, and Piotr managed to obtain the data he needed. So measuring at such temperatures, well, I don't know about some alternative ways to measure at 100 Kelvin and to write it down to the spectrum simultaneously. So that's a really world-class experiment, and if this installation still works, I would come with my samples, and I believe there are many researchers that would like to cooperate on this topic with Piotr. And additionally, I cannot but mention this interesting approach to the representation of data simultaneously registered in NMR and absorption. This pseudo-formula of representation of spectra, that's a mathematical model, so it all equals to the spectra of NMR and this, and without placing them side by side, there was a folding that allows to show everything on one picture and to understand the regularities at once. Obtaining experimental data is hard, but sometimes understanding them is even more complicated. And this beautiful approach from the point of view of mathematics should be noted as well. From the point of view of remarks, I did not find any drawbacks. Certainly I managed to find some misprints, but not as much as Sergei Yulievich. But I wanted to mention three terminology comments. One of them is just negligible. Why did you use this word complex, which is associated with complex of charge transfer instead of associate that is frequently used to describe hydrogen bonds. And a second terminological point, I hope I can add up this one as well, on the use of word anti-cooperativity, because I used it in my thesis once, and I got a criticism that this term is not correct and we should use negative cooperativity. And I saw this comment twice, and maybe there is difference here. And for me, I did not understand it quite well for myself. And now looking at this thesis, I thought maybe Piotr will have a vision why you write anti-cooperativeness instead of negative cooperativeness, because it seems to me that there may be some difference. Thank you, Valentin. Piotr? Yeah, comment on the technical work. In current war conditions, we work up until the first breach, because these firms stopped cooperation with Russia. So now about your remarks. I was a kind of a opportunist, and I used the term that is used in a hydrogen-bound community, so to say. This word complex has an overlap with this term in other fields of chemistry. Is used as both in Russian and English literature as a reduced formula for a complex of hydrogen bond. And it is used quite frequently that sometimes all the other words are just thrown away, and you start using complex, because that's why it happened. For me, it was associated with associate. But I could have foreseen it, saying that I'll just bear that in mind. And the second remark was on anti-cooperativity and negative cooperativity. That's a translation of the only term that I found for hydrogen bond. That's well, I haven't seen negative cooperativity, therefore I used anti-cooperativity. And if I was misunderstood as a result, well, that's a surprise. Yes, every field of science has its slang. Okay, I have no other comments, therefore I switch to the conclusion that the thesis by Pyotr Tolstoy meets the requirements of the order on the procedure of granting academic degrees at St. Petersburg State University, and Pyotr Tolstoy deserves the academic degree of Doctor of Sciences in Chemistry and specialization Physical Chemistry. Articles 9 and 11 of the above-mentioned order are not violated. And also this thesis can be considered a huge contribution to the field of science. So I believe that Pyotr Tolstoy deserves the degree of Doctor of Sciences in Chemistry. Thank you, Valentin. Now, dear colleagues, we've already heard half of the reviews, and now we switch to the reviews of colleagues who work remotely today. So please, Professor Kiselov. Thank you. First and foremost, I would like to thank you for the opportunity to participate in this defense. That's quite an honor for me. And I agree with colleagues who mentioned the contribution of Piotr to this field of science, and I really agree with that. And I won't go too far, I just wanted to say a few words about my impression. Indeed, reading this work, I understood that I liked it a lot, and I really enjoyed reading the thesis. And if we talk about the relevance and novelty of this work, indeed, regardless of this importance of understanding of hydrogen bond formation, there are a lot of works published on the topic with Raman spectroscopy, with computer modeling. Still, what was done in NMR spectroscopy was not sufficient up until Piotr started working on that. And since then, he made a lot of discoveries, and that's a very in-depth research. And if we talk about some particular impression, I was particularly impressed by NMR monitoring of anti-cooperative behavior of hydrogen bonds and clusters. Some time ago we tried to work on that, but we were not successful. And the fact that he managed to do that successfully, that's really a support for us. The thesis is really written well, with a good Russian language, and I believe I mentioned it to Piotr that it would be nice if this thesis would become a monography in the near future, because this monography would be very useful for people who are interested in this field of science. There are no such monographies, and certainly it would be nice to have one. Now I shift to my remarks. I had few of them, and some of them are associated with an accuracy of narration, so I would omit them, because I believe there is no need to mention them at all. I just wanted to mention the second comment on molecular dynamic method that you mentioned. So the author uses non-empirical method of molecular dynamics in the implementation of CPTK to study the dynamic characteristics of hydrogen bonds. As Carper-Nell methods are quite costly from the point of view of computer resources, the maximum achievement is 10 picoseconds, and this time is not enough to study the lifespan of hydrogen bond. And in this regard, it's unclear why you did not conduct modeling using classical molecular dynamics that would allow to assess the lifespan. And sure enough, the results of this modeling, jointly with non-empirical calculation and experiment, would allow to analyze the dynamic characteristics more specifically. Thank you. Piotr? Thank you, Mikhail. As for the modeling, I don't know where to look in order to look in your direction, because you're on every screen. So I look into the I will look at the listeners. In order to model such complexes correctly, complex with protons divided into between two heavy atoms, where prototropic tautomerism and proton transfer processes play a key role. Molecular mechanics in classical approximation will not be suitable, because we have breakages and bond formation, and even dissociation is possible depending on where bridging proton stays. Therefore, we would have to include the QM part, QM calculation, and this would make it very costly. And modeling microsecond like that maybe would be successful, but as for the assessment of the lifespan, it is a millisecond. Therefore, representation of these calculations would still be questioned. But I will agree with you, saying that if we shift to the consideration of complexes without proton transfer with weaker bondage, the value of using molecular mechanics would proportionately grow, but not for those complexes that we considered, unfortunately. These are extremely strong complexes. Did I answer your question? Yes? Sure, thank you. Then I shift to the conclusion. Overall, the thesis is written on a relevant topic with a nice language, and it forms a new scientific field for development. And the results of the thesis are credible. A thesis by Peter Tolstoy, titled Diagnostics of Complexes with Hydrogen Bond and Proton Transfer Using Low Temperature NMR Spectra, meets the requirements of the order on the procedure of granting academic degrees at St. Petersburg State University, and Peter Tolstoy deserves the academic degree of Doctor of Sciences in Chemistry and Specialization 144 Physical Chemistry. And Articles 9 and 11 of the above-mentioned order are not violated. Thank you. Thank you, Mikhail. Next review. Alexander Kuchin. Thank you. Distinguished Chairman, distinguished members of the board. I wanted to greet you from the city of Volgograd, where I currently attend medical chemistry conference, and I did not mention it by chance. I just wanted to emphasize the practical value of the work that we are discussing today. The application of those correlations that were demonstrated by the author using hydrogen bonds is quite applicable and is already used to describe biomolecules and to understand those problems that emerge in the development of medical chemistry. So thus, I wanted to confirm the high practical and scientific value of this work. And here we should mention yet another thing: quantitative indicators of the thesis. I believe no one mentioned that. There are more than 600 quotations in the list of literature, and it's clear that it's a really huge work. And the material that was presented is really quite demonstrative, and it shows the relevance of the study. And I should also mention that here 200 different complexes were studied in the thesis. That is all, and it also characterizes that volume and quality of work that was conducted. And I cannot but confirm that during the discussion, you already mentioned all those questions that I had while reading the thesis. And I would like to support my colleagues and say that this thesis is beautifully written, though the presented volume was pretty significant. And maybe those limitations that were imposed by the Higher Attestation Commission, no more than 300 pages, maybe these requirements are quite expedient, not to go beyond the limit. But still, all the material is quite original and interesting. And now I switch to the fact that I have no principal criticisms, key criticisms, and I would like to support the words of my colleagues about this research. And the majority of criticisms that I had were already mentioned like the understanding of, so like you've already described the complex, because we see terminology a bit differently, but still I believe that Piotr explained his understanding here, so I was satisfied. Though I make this conclusion that you should have done it in the introduction, and in this case it would be pretty nice, as well as the assessment of the values of expected error, so everything that is associated with physics and chemistry of those parameters of description, with geometry, with the length of bond, and so on. So that was already mentioned in answers. And here I would like to particularly mention one comment that I made. So the majority of correlations of spectrum and structure was obtained for the complexes with hydrogen bond in solution. And there is a question on the applicability of these correlations to complexes in crystals. Maybe that's an interesting question as well. Maybe you'll answer. Yeah. Yeah, sure. I've already commented partially this question when other colleagues asked about it, so maybe I'll repeat a bit. The first correlation of hydrogen bond was obtained in crystals. And then these results were transferred for solutions, for liquids. And when we switch from one aggregate state to another, correlation remains, but the geometry of bonds in the complex may change significantly, and it leads to the shift of point in the correlation, but not to away from this correlation. And this is the result of two principal points, key points. First of all, local spectral parameters of NMR that actually reflect the local electronic structure in close proximity from the observed nucleus, and the fact that light bridge particle manages to adapt to the moment it manages to adapt, as well as NMR parameters, preserving this correlation. In the process that would be quicker than the ability of bridge particle to move, the correlation would be distorted, but there are practically none of such processes. Okay, thank you. And I believe I had yet another comment. So it was already mentioned that the author deserves gratitude and praise for the fact that he developed a unique sensor, and the work that was conducted, it should be protected somehow. And here I give my opinion that the achievements should be defended, and we have copyright for what we publish. And when we have practical implementation, certainly it should be discussed with producers. But in this case, I wanted to say that our Russian patent law is developed pretty well today, and you can get a patent and coordinate it with the producers, but still the principle and the mode could be patented. Though I can also recall two other types of intellectual property protection. That's know-how, certification, and that's what we use at our institute, and also a model. A utility model. So I believe that that's a unique work that should be protected. So I ask you to pay attention to that, and maybe in the future you will get all the necessary protection. Yes, maybe I wanted to comment. No, I can just tell you that I should maybe get back to this question and think about it. Yes, I believe we can discuss it separately. Maybe I'll give you some useful information on that. And now this formal part that I need to mention. I believe that the thesis by Pyotr Tolstoy, titled Diagnostics of Complexes with Hydrogen Bond and Proton Transfer, using low temperature NMR spectra, meets the requirements of the order on the procedure of granting academic degrees at St. Petersburg State University. And Pyotr Tolstoy deserves the academic degree of Doctor of Sciences in Chemistry in specialization 144, Physical Chemistry. And Articles 9 and 11 of the above-mentioned order are not violated. Thank you. Thank you, Alexander. Next review, Yuri Turubayev, please. Yuri, the sound. We can't hear you. So we can't hear you right now, so please check the sound. Do you hear me? Yeah. That's really a fascinating and relevant work. Colleagues have already mentioned that. And I can just add my impression that some of the chapters of this work could be defended separately as separate studies. And overall, I believe that this work is more than decent. And when I read it, I thought about the use of these experimental achievements as applied to our objects with halogen bonds. And I did not have a lot of criticisms. And these criticisms are mostly dealing with the style. And I can briefly mention them, though they were already listed. Yes, you can just mention them briefly. Okay. So there was a question on the contribution of halogen and hydrogen bonds in the system with HF2. But still you return to this topic after 15 pages when we talk about C-chlor-4. And as for that, you mentioned that that's an inert solvent, though it is inert in classical systems and in molecular chemistry. It is an active ingredient, and we can check it in the chemical bank how many times it was used in supramolecular systems. then when you described fluoride-bearing systems, you considered fluoride, and a fluorine atom is considered as a donor of electrons. And acceptor of hydrogen bonds. These are quite exotic systems. Fluoride ligands were considered by Lieberman as acceptor halogen bonds, so I believe you should have paid attention to that as well. I had no other significant comments, and even these comments do not compromise the overall high value of this work. And in conclusion, I wanted to say that the thesis by Fyodor Tolstoy, titled Diagnostics of Complexes with Hydrogen Bond and Proton Transfer Using Low Temperature and Mass Spectra, meets the requirements of the order on the procedure of granting academic degrees at St. Petersburg State University. And Fyodor Tolstoy deserves the academic degree of Doctor of Sciences in Chemistry in Specialization 144, Physical Chemistry. And Articles 9 and 11 of the above-mentioned order are not violated. Thank you. Thank you, Yuri. Piotr, you can answer. Yes, Yuri. As for what you mentioned about halogen bonds and tetrachloride carbon, I can just say amen. Yes, that's it. And as for the structure of narration, I did not manage to create a kind of intrigue that was an open secret. You know, as I described it 15 minutes after that. So I just agree with you. But I cannot but mention that these results are not that obvious if we talk about the scale of effect of these halogen bonds on the position of on the overall position, and this effect in the scale is higher than hydrogen bonds. It was quite unexpected for me. So this ensemble of geometry is considered in very few works. And as for the most state-of-the-art ones, we just remember Daniel Sebastiani group work. That is why we discussed it with Svetlana Kulayeva, his student, because we wanted to understand what values we are talking about. And it turned out that we didn't have a lot of outstanding articles on this topic, but as for the formation of tetrachloride carbon, as for the formation of the chloride carbon, certainly that's not a discovery for an expert in the field. Yuri, are you satisfied with the answer? So we can't hear you. So you agree, okay. Okay, our next report will be delivered by Georg Denogulyan. Thank you. Distinguished colleagues, it seems to me that all of us enjoyed this defense a lot, and we enjoyed both the material that was presented, because Piotr has brilliantly delivered his report, and we all enjoyed the presentation because he simplified his work even more. And I believe that we all today enjoyed the topic, including Pyotr Mikhailovich, who has not just brilliantly described his achievements, but also enjoyed well answering the questions, so you could tell it for sure. And as I am one of the last board members to present my review, and there is just the chairman's report left. Therefore, everyone has already described the positive aspects of this thesis. Therefore, I'll try to briefly dwell upon separate aspects. Certainly, I am to start with the fact that this work is relevant and it is in the front line of those studies that are ongoing for non-covalent interactions. And in this field, we see the study with methods that Piotr described. And sure enough, that's a new achievement in the study of NMR, not just for the reason that Piotr studied the field of low and super low temperatures, but also for the fact that he combined it with unique instruments that were developed separately to cover those hydrogen bonds. The change dynamics in systems and the change of conditions. And out of the list of experimental materials and those summarizations that were prepared by Piotr, we see that this is quite an outstanding work in a field that it was created nuclear magnetic resonance in particular conditions. Therefore, I will not be able to dwell upon those points that impressed me most, though I still want to mention that for me it was really fascinating to read about correlations in NMR and the chemical shift, the spin-spin coupling when studying deuterium and hydrogen bonds, and also the study of the system that imitates the chains of strong hydrogen bonds in the active center of yellow protein. These results were partially used to construct the catalysis mechanisms, and sure enough, they are of interest for practical implementation and use in biological systems. And I would like to separately mention, as the previous speakers, the fact how Piotr registered spectra in NMR spectrometer. That's a unique method, a risky one. However, Piotr still managed to enjoy this drive of experiment. And if we talk about things that were not mentioned by colleagues, I cannot but say that each chapter is summarized with conclusions that allows the reader to assess the correct summarization of the author. And what else do I want to mention? Not standard structure of the thesis. Petr took away one of the mandatory sections, literature review, and this does not compromise the quality of the work. That's just the fact that the author is sure that it should be like that. Literature material is integrated into the experimental data and is given together with experimental data prepared by the author. And the thesis, it was already mentioned that there were a lot of literature sources, 600 sources, namely, and thanks to that, we can be sure to say this makes the thesis a valuable source of information, and it demonstrates that the author understands the topic pretty well. And once again, maybe I'll repeat myself that this thesis is a bit lengthy because there are 460 pages of it. That's a bit too much, but maybe Petr here also enjoyed his particular skill in working with this material. And in conclusion, I need to give my remarks. And certainly these remarks are quite formal. And certainly they do not influence the general quality of this work. As for the first question, in Chapter 2, you gave a model of bond order for interatomic distances, and it does not take into account the deviation of the angle from 180 degrees. So how justified is the use of these ideas? In Chapter 2.3, you offer to define the geometry of hydrogen bond based on isotopic effects on the chemical shift of carboxyl carbon. And you give acetic acid as an example. And it seems to me that you could have expanded it to different carbonic acids, amino acids, and other acids, benzoic acids, that you studied in other chapters. And finally, it seems to me that the language is really beautiful, the language of the thesis. There are a lot of diagrams and figures that simplify the understanding. However, as any major work, this work has some losses, and in the quotation list I've seen certain losses. Not everywhere you mentioned the intervals for pages, and in Soviet period we paid a lot of attention to that, so I believe I had to mention that. And surprisingly, in this list I've seen the articles of the author. These are references 23 and 25. And in conclusion, I want to give my opinion, and after that I believe Petr will have an opportunity to answer these questions. Or how should I make it? Yes, Gevorg, you can read the formal part. Yes, and after that, Piotr will answer the questions. Okay. Based on the above mentioned, I believe that the thesis by Pyotr Tolstoy titled Diagnostics of Complexes with Hydrogen Bond and Proton Transfer using Low Temperature and Mass Spectra meets the requirements of the order on the procedure of granting academic degrees at St. Petersburg State University. So I announce the second technical break. Yes. And I believe that Pyotr Tolstoy deserves the academic degree of Doctor of Sciences in Chemistry in Specialization 144 Physical Chemistry. And Articles 9 and 11 of the above-mentioned order are not violated. Thank you so much. Gevorg. Piotr, you can answer the questions. Yes, thank you very much. Gevorg Grachevich, you are the 9th. Therefore, I've already answered part of your questions, some of your questions, but I will just say that, I can just say that I agree with you as for the technical remarks. I agree with all of them. And I agree with the fact that that the thesis had more volume than it should have. But I just would like to answer one thing. I wanted to see to check some other carbonic acids, not just acetic acid, amino acids, and benzoic acids. But maybe I'll leave it for the future. Maybe this will be a diploma work for some of my students. And I hope that we will continue studying this field. And yet another comment. It seems to me that as a result, we'll see that the trends stay, functional dependencies stay, and all the scale multipliers may change a bit. As for the references to my works, I had 2 points. These references 23 and 25. These are references to the works based on which the thesis is written. They are not just given at the start of the list. And then I had references to the works in which I participated. I just took one parameter there, but I did not describe them fully in the thesis because I didn't have a link to the experimental data that I needed. Those were just my works, and I had to refer to them. So that's the only way out that I found. And now you mentioned that it looks strange. Yes, it is. And I agree with other technical remarks. Gevorg, are you satisfied with the answers? Yes, sure. Okay, thank you once again for your review. Dear colleagues, I'll Now it's my turn, and in this work I wanted to mention 2 points. Peter studied one of the most fundamental processes. One is electron transfer, and the second one is proton transfer, and all the reactions undergo these 2 elementary stages, and so that's why this work is relevant. And essentially this work demonstrates and illustrates a genius principle of linearity of free energies of Gibbs when we deal with energies. And these values, chemical shift, spin, coupling, angles, so that's the reflection of energy. And that is the essence of work. And that's a brilliant work. And as a chemist, you know, I waited for these words about energy, but you did not mention it. Therefore, my remarks are associated with the energy block, though you did not describe the skills in the beginning of the work, just geometry, angles, and the content. But still, I have 2 blocks of questions. The first is associated with energy, taking into account the experience that you obtained, the experimental experience and the literature data. What are the activation barriers for the transfer of proton? Yes, can I answer straight away? Yeah, let's go step by step. Yes, we can assess them. For complexes with strong hydrogen bond, it can be assessed, this energy of activation of barrier. We can assess the height of barrier of activation, and it can be assessed from the bottom, the speed of this process, and then we'll shift to energy. It can be assessed from the bottom. The process is quicker than hundreds of microseconds because NMR is averaged. It is slower than femtoseconds because in UV everything is demonstrated. And the speed of the process in quantum chemical calculation is comparable to the time of rotational diffusion of the molecule of solvent, or its shift due to diffusion to the distance of its own size. That's a picosecond. And picoseconds were transferred into energy, and we get a kilocalorie. And 1-2 kilocalories, these are the barriers. So that's low barrier process. Yes, it is. That's the characteristic of the chosen systems. In other systems, we may have different values. So that's the characteristic of strength of bond and the opportunity of molecular so-called skeleton to adapt to geometry and to approach closer so that this barrier will be close. And if we squeeze a dominant acceptor, regardless of how you change electronic values, the transfer will be large because it will actually be associated with dissociation of proton up until proton affinity in the marginal condition. But as for the strong bonds, that's 1 or 2 kilocalories. And based on NMR data, can you assess the energy of the hydrogen bond? Because you give, there are wide ranges in literature, but based on your data, we can. But all these works were not included in the thesis, yet we have them. And I'll briefly tell you that we have a range of literature sources, and they all mean the same. The change of chemical shift of the bridge proton and the strength of bond is associated in a linear manner from 0 to maximum strong. And the angle of this curve depends on the chemical nature and on the test set of the correlation. But if we generalize, we see that for hydrogen bonds that are strong and medium, for OH and NH, donors and acceptors of proton, we get 1.5 kilocalories. So that's 1 or 2 kilocalories here. So that's it, what we can say on the topic. Though directly these results were not included in the work, and if they would, Georg would refuse to read this work. Okay, thank you. And I had questions on aces that you used and bases that you used. And those systems that you used, the strongest acid is HBr4. And if we use trifluoromethane methane acids. So, well, intuitively, you see this would be a good source of complexes and bases, and it would be a good source for practically free protonated bases as HBF4. We did not do that, maybe because it was, a kind of inertia of work and lack of fantasy. But still, I believe homoconjugation of is very interesting here. If we look at the literature sources, we see that this solvated proton is something that people did not previously work on. While in superacid self-dissociation is small. It starts when a base enters, when there is a transfer to the base, then solvatation starts. And here we see this superacidity mechanism, as well as activation. Then another question was dealing with the system with fluorine. We have water there, therefore it can distort the systems that you study, especially beta-9 complexes. Maybe H fluorine would be more would give more significant results. Well, initially we had it in the water solution, and H fluorine stayed there. You can leave it as a powder, and if you leave it as in solvent, maybe we'll get a packed glass. But if at low temperature, it's not that risky. You can distill water and then stay at low temperature and get the NMR sample. And as for trace water, we get them in freons when the temperature is below 150 degrees Kelvin, minus 150 degrees Kelvin, if nothing holds this water strong, because the strongest bond is with itself, and when it crystallizes, we see that it is no longer there in the solution. Okay, question on acids. Another question on acids. Carbonic acids form strong hydrogen bonds, and their diamonds are stable. And you used pentachloride chloride of antimony. So, well, quantum chemical calculations for phosphinic acids reproduce that there is hydrogen bond there, and experimental measurement and chemical shift in acetic acid. Well, they're low pole, and that is something that you don't expect for such an acid. There are rather hints at the formation of hydrogen bond. And I agree with you that the combination is a model of monomer of acetic acid, and that's not a self-associate model. But both sides, they have this antimony pentachloride covering them, and they're closed for self-association. And there's also carbonyl couple pairs there. Okay, thank you. And a question on amines. Acetic acid complexes with different amines, and these amines are not symmetric. They're chosen heterocycles, and if you take ammonia, it will have symmetric cation. Maybe you can use NMR data to make some conclusions on that. Well, I would presume that there are two things here. One thing is that it's possible that the solubility of this complex will be significantly lower than in a complex with pyridines. Therefore, I don't know how much will dissolve. And if the proton will shift to ammonia, the resulting substance will likely rotate quite quickly, and all the four protons will stay chemical equivalent between 3 free and 1 bound. And we'll see the spin-spin interaction with nitrogen in the center due to the symmetry, and maybe N14 will allow us to measure the spectrum. It will be low from this ammonium. So maybe we'll have all these manifestations, but practically, maybe at 100 Kelvin, the solubility will not allow us to do that. Okay. Now I shift to the conclusion. A thesis by Petr Tolstoy titled Diagnostics of Complexes with Hydrogen Bond and Proton Transfer using Low Temperature NMR Spectra meets the requirements of the order as of November 19th, 2021, number 11181/1 on the procedure of granting academic degrees at St. Petersburg State University, and Petr Tolstoy deserves the academic degree of Doctor of Sciences in Chemistry in specialization 104 Physical Chemistry, and Articles 9 and 11 of the above-mentioned order are not violated. Distinguished colleagues, is everyone satisfied with the answers? Everyone. Remote colleagues who worked remotely, you're also satisfied? Okay, thank you. Do we have anyone willing to ask a question or to comment? None. Okay. Did we get any questions during the broadcast? No. Okay, we can shift to the speeches. Thank you so much, dear colleagues. I'm Vadim Kukushkin from St. Petersburg State University, and I wanted to recall 3 people, classics of chemistry. First one, Yuri Zhdanov, corresponding member of the Russian Academy of Sciences, rector of the Rostov University, who was a very extravagant man, and he loved disputes. And he opened up any thesis, and he said that at any thesis on any page I will find 2 mistakes, and no one won in this dispute. And the second classic is academician Rozуваev, the graduate of our university, who established the institute that Sergei represents. And unfortunately, I do not remember who was his a PhD student, but Grigory found and asked 287 questions. It's clear why Sergei Yulievich sticks to sense with his traditions of this institute and counts all these mistakes so well. So summing up the first 2 approaches, I can say that if there are no mistakes, I would be really surprised with this fact, not with the fact that they are there. And they're quite natural both for science and for scientists. But I believe they are negligible. And finally, the third classic is academician Moiseev. This was the shortest speech possible at the dissertation board that I've ever heard. He took the microphone and said, "Gentlemen, I had no significant comments for this thesis, and as for the negligible ones, I don't want even to mention them." And this was it. Therefore, taking into account that I don't have such a mantra, for conclusion, I can just say that Piotr really deserves the degree of Doctor of Sciences. Okay, dear colleagues, thank you. Georg Gracevich, please turn on the camera, because we're going to shift to the vote. I believe my camera is on. Yeah, he was there. Yeah, yes. Just a second. And right now, yeah, that's okay. Okay, dear colleagues, summing up, we need to mention that Piotr managed to answer to all the 10 doctors of science and of sciences and answered our questions decently. Now, everyone needs to answer if he or she has any comments on the procedure of our defense. So please. Alexei? No. Sergei? No questions. Ekaterina? No questions. No objections. No objections. Mikhail Kiselov? No objections, thank you. Alexander Kuchin? No objections. Yuri Turubayev? No questions. And Professor Donoglan? No criticism. Okay, I have none as well. And now let us shift to the vote. Distinguished colleagues, we can organize a closed session. In this case, we will need to organize a technical break in order to discuss everything in a closed manner, or there's no need for that? Yes, no need for that. We can shift to the vote straight away. Okay? Georg, don't be too fast. Everything is written here in our agenda. So, dear colleagues, it's 20 minutes. 20 minutes to 4. And I raise a question on the award of the academic degree of Doctor of Sciences to Pyotr Tolstoy. And I would like to emphasize that voting for the award of the academic degree, each member of the board agrees that Article 11 of the order is not violated by the candidate. And let me quote it. In the thesis, the applicant for an academic degree is obliged to cite the author and or the source of the materials or individual results borrowed using the results obtained by the applicant personally or in co-authorship. The applicant for the degree is obliged to note the circumstance in the thesis. And let me remind you that the decision of the dissertation board on conferring the academic degree is positive, provided more than 50% of the board members, but not fewer than 3 people, voted in favor, in conformity with Section 817 of the Order on the Procedure of Granting Academic Degrees at St. Petersburg State University. Now let's shift to the vote. So, Professor Viktorov, I vote for the award of the degree. Okay, Professor Adonin, I also vote for the award of the degree. Professor Bartoshevich, I vote for. Professor Kitkov, I also vote for the award of the degree. Professor Novikov, I vote for the award of the degree. Professor Kiselov, yes, I support this work as well. Professor Kuchin, I also support this work. Professor Turubayev, I also vote for the award of the academic degree. And Professor Donoglan, I also vote for the award of the academic degree, and I chair of the board. So I, chair of the board, also vote for the award of the academic degree. Thus, dear colleagues, I would like to announce that out of the 10 members of the board, 10 voted for the award of the academic degree and no one voted against it and no one abstained from the vote. And in conclusion, I would like to say that we decide to award the academic degree of Doctor of Sciences in Chemistry in Specialization 144 Physical Chemistry to Pyotr Tolstoy. And let us congratulate Mr. Tolstoy and give him the floor. So please, you have the floor. Dear friends, out of the many people that I'm grateful to, and many of them are listed in the end of my thesis, but not everyone, because you can't list everyone, and some of them are here, and I hope that to thank those who are here personally after the defense. But now I would like to mention 2 people. One is Professor Denisov, and another one is Professor Limbach. These people were my consultants during my PhD thesis preparation, but still they influenced me so much from that point up until now. These are not just talented scientists. These are people that are kind and really humanistic, and the most pathetic way. And because of them, you wanted to stay at the university. And I hope that finally we'll have an osmosis. And if you are a conductor, not a recipient of this opinion, I would like to tell you one thing. If you have some humanistic urge, don't be silent. It's important for everyone. Thank you, Piotr. And we congratulate you once again, and we wish you all the success. Dear colleagues, we therefore close our session, and I would like to thank our remote participants, and I would ask you to switch off